In the previous video, we discussed about the concentration of electrons in thermal equilibrium, that is N0, and we derived it from GCE, that is the density of states in the conduction band multiplied with the Fermi-Dirac distribution function, which gives you the probability of distribution of electrons in the energy range EC to infinite. The same way we can find out the expression for the thermal equilibrium concentration of holes in the valence band by just multiplying the density of states available in the valence band with the probability that a state is not occupied by electron, or we said the probability of finding the hole, which we said 1 minus f of e, so 1 minus f of e. So this gives the probability of finding the hole, and this is the density of states in the valence band over the energy range in the valence band, which varies from minus infinite to the maximum value of valence band energy, which is EV. So we will find out this expression mathematically, and we'll get the expression for P naught. So to start with, we have the Fermi-Dirac distribution function, which is f of e is given by mathematically 1 divided by 1 plus e to the power e minus ef divided by kt. So this is the Fermi-Dirac distribution function. Then we can find out what is 1 minus fe. So 1 minus fe is 1 minus this whole thing, that is 1 plus e to the power e minus ef divided by kt. Okay, so that further we can rewrite this as 1 plus e to the power e minus ef divided by kt minus 1 whole divided by this 1 plus e to the power e minus ef by kt. Okay, so which can further be simplified as finally we can write this as exponential e to the power e minus ef divided by kt whole divided by this as 1 plus e to the power e minus ef divided by kt. Okay, now dividing both the numerator and denominator by same factor, that is e to the power e minus ef by kt. So dividing the whole thing with e to the power e minus ef and divided by kt, and here also dividing with the same e to the power e minus ef divided by kt, we can obtain we can obtain we can obtain um, this as 1 divided by 1 plus exponential of e to the power ef minus e divided by kt. So this is what we got as 1 minus f of e. So this is your 1 minus f of e. This is 1 minus f of e. So using this 1 minus f of e under the condition of Maxwell Boltzmann approximation, using Maxwell Boltzmann approximation here, we can reduce it to what is the Maxwell Boltzmann approximation, how we can apply Maxwell Boltzmann approximation. For energy states in the valence band, we said the valence band, the structure of the valence band is this is the structure of the valence band, where the maximum value of energy in the valence band we defined as EV, and this we have taken as minus infinite. So any value you can take here is, let's say, E, any energy state corresponding to an energy value is E, and we can write this E is always less than EV. Okay, so we can take if EF, the Fermi energy, minus EV is much larger than KT, the Boltzmann constant, multiplied with value that is absolute temperature at 300 Kelvin. This is found to be 0.025 electron volt, which is very less, and hence we can take this assumption EVF minus EV. EF is somewhere in between EC and EV. So we can write, if this is much larger than KT, then we can write EF minus E is also much larger than KT, because we said E is less than EV. Okay, so this way we can write exponential of EF minus EV, EF minus EV divided by KT will definitely be much larger than 1. So using this, we can write 1 minus f of E, 1 minus f of E is equal to 1 divided by 1 plus exponential to the power EF minus E divided by KT, which is nearly equal to, ignoring the value of 1, which is nearly equal to, this one can be ignored here, so which will give us a value x e to the power minus of EF minus E divided by KT. So we will use this as the distribution function for holes under the condition EF minus EV much larger than KT. Under the condition EF minus EV is much larger than KT. So using this value of 1 minus f of E, we can now write P naught. If I will find out the value of P naught, then it is P naught, the whole concentration in thermal equilibrium in the valence band, is given as integrated from minus infinity to EV, substituting the value of GVE, which is 4 pi divided by h cube. This is twice of mp star, effective mass of hole, to the power 3 by 2 square root under EV minus E exponential to the power the distribution function, which is minus EF minus E divided by KT. Okay, this DE. So we will just mathematically simplify this so that I can write in the next step, take the constant terms 4 pi by h cube and twice of mp star to the power 3 by 2 out, and then exponential of EV minus EF, the same way that we did it for N0, finding N0 divided by KT. Okay, and this exponential term here we are breaking it. Okay, and here within integration, let's write minus infinity to EV, and then here EV minus E to the power 1 by 2, which is here. Okay, and then exponential of the remaining term after this exponential term, exponential of E minus EV e to the power E minus EV divided by KT dE. So now if you see, here we got minus EV, here we got minus EV, and you got plus EV here, cancel, and you got E minus EF, which is the one we have written here, E minus EF. Okay, it gives the same value. and this exponential EV is the maximum value which is constant, EF the fermi energy level which is constant, KT is constant, so this whole constant term is taken outside here. Okay, so it will be easier to find the integration here. Okay, so we can write this as to find the integration here. To find the integration, let's take EV minus E divided by KT is X. So if I'll find differentiate both the sides, DE will be minus KT dx minus KT dx. So if you'll change the limit for when E equals to EV, we have X is 0. E equals to EV, if I'll substitute here, then X equals to 0. X is 0. And if for E is infinity, for in E infinite minus infinite, we have X is plus infinite. So we can rewrite the above equation as P naught. Okay, E is given as 4 pi by h cube, the constant term, and then twice of mp star to the power 3 by 2 and exponential of EV minus EF divided by KT. Okay, then the integration here, for minus infinity we have plus infinity, and for EV we have 0. So 0. Then substitute here x to the power 1 by 2, KT to the power 1 by 2, and then e to the power minus x, and then d is minus KT dx. So this is what we got for P0. Further simplifying it, we can write it as P naught is we can rewrite it as 4 pi divided by h cube twice of mp star to the power 3 by 2 exponential e to the power ev minus ef divided by kt. Then we have this kt to the power 1 by 2 and that minus kt, so we got kt to the power 3 by 2, and within integration 0 to infinity, the limit, we have this x to the power 1 by 2 e to the power minus x and dx. Okay, so here using again the same gamma function that we have already used, this is found to be root under pi divided by 2. So substituting this, we have p naught is just 2 into 2 pi mp star, this is kt, divided by h square, this whole thing to the power 3 by 2 exponential of, in bracket we have ef e to the power ef minus of ef minus ev divided by kt. Okay, so now this is again in the form of some function which we said the density of states function, and this one is the distribution function. This is the distribution function. So product of, so whole concentration is again the product of two terms. One is the effective density of states in the valence band, and the other is the distribution function. So here we can again write this as NV, this whole thing is for NV For this we wrote NV, and this one the remaining is we have exponential of a minus of EF minus EV divided by KT. This is the distribution function. So we got the equilibrium hole distribution in the valence band in thermal equilibrium condition. So this is the expression for P naught.